Guy is going to talk about some new spec work and some new implementation that he has been working on for the last few months or years or something like that. It's pretty fantastic. When I saw it, the first prototype, it blew my mind, and I thought, no, Guy needs to come to NodeConf and show it to everybody. So Guy is going to talk about this new spec called WebAssembly Component, right? Is that true? Okay. And yes, here is Guy.
So thanks so much for the introduction, Matteo. The talk I'm giving, as you mentioned, is an introduction to WebAssembly components, and the assumption that most here would be relatively unfamiliar with the proposal. So I'll start with a kind of a motivation about what they are and why they're useful. This talk is going to be demo heavy as well. So hopefully, with some luck, those demos will work correctly. And then we can talk about some of the future potential of these proposals and some of the upcoming milestones. So to start off with the motivation, WebAssembly and JavaScript are these very closely related specifications. And WebAssembly originally coming out of the ASM.js effort many, many years ago, which is a subset of JavaScript that could be optimized and sort of eventually became its own whole ecosystem. But we're kind of separate ecosystems, separate communities, and the relationship between JavaScript and WebAssembly is not as close as it really should be, given this kind of historical situation. What do I mean by that? Well, ideally, we would be able to just transparently use WebAssembly from JavaScript in a way that we could treat WebAssembly just like another import, another module import, and you would get something that would represent the sort of high-level usage you would typically have for example, a third-party library. But in reality, when you do that today, if you have a library that you're loading into your application that's using WebAssembly, there'll be a lot of JavaScript glue code, in scripts and outputs and things like that that'll wrap all the WebAssembly, and internally it'll be doing a lot of setup. Possibly setting up some WASM workers and running a whole bunch of stuff in the background. And that's great. We've been able to build incredibly powerful applications with WebAssembly, and there's a lot that we can do with it. But there's this problem of glue code, and that introduces these subtle frictions. So this is an example of what I mean by that, the sort of bare minimum of some of the frictions you get with the glue code. And this is an example of loading ESBuild WASM and a sort of a very bare minimum version of the sort of glue you need. In this example, we're using the URL spec to find the esbuild.wasm file. We're using import.meta.url to find it as a relative URL. We're using the fetch specification to be able to get those bytes. We're using WebAssembly, Web API, and then we're able to instantiate ESBuild against its own runtime. Before we can get the transform function, and then we probably still need some wrappers to be able to provide a high-level transform function. So there's some other assumptions here that for example, if you're running in Node.js, will you even be able to use the fetch API? It's relatively new in Node. If you're on other runtimes, will you even be able to fetch file URLs? Because import.meta.url will be a file URL. Will your bundler understand this? And you introduce all these subtle frictions along the way that you then need to branch this wrapper code to be able to deal with. So when you have this application, you then want to be able to distribute it on, you're going to want to run this code in all these different environments, for example, on Node modules, in browsers, in Node.js and other runtimes, and in WinterCG environments. And so when you try to run it in all these different places, you end up with a lot of branches to be able to support all the different ways that WebAssembly might run in these places. So how can we simplify that glue code? Well, we've got two proposals in the works at the moment. We've got the WebAssembly ECMAScript module integration, and we've got source phase imports, which landed at stage 3 at TC39 in July. And if we apply these specifications, we can actually simplify this existing glue code. Using this direct ESM integration, we could replace that with something like this. So instead of using the fetch and URL and local loading, we could directly import that ESBuild source, instantiate it locally, and then get the transfer method. And that cuts out a whole bunch of those initial frictions about where you locate that asset, how bundle is supported, et cetera. By making it a static part of the module system, it's something that can be supported across environments quite in a relatively standard way. But there's still a little bit of glue here as well. What we'd really like is something like as simple as just importing a transform function from a WebAssembly binary. So what would it take to get us to that kind of a level of simplicity? And so the argument is that that's very much sort of a motivation for the component model, which is that you have these rich language-agnostic WebAssembly interface types that solves for the embeddability of WASM. So you can be able to have, kind of similarly to Michael was talking about earlier, that you want to have these first-class data types that you can pull into your WebAssembly module so that it can speak the host native types. And you can support the kind of interfaces that you would write in JavaScript applications today. And we have things like support for resource objects. The second thing is module linking. So this is first-class instantiation. So if you look at this glue code, the other part of what this glue code is doing is it's having to instantiate that WebAssembly module against the runtime that runs it. And so that's something that you can only do in JavaScript today. So with the component model, WASM gets the ability to do its instantiations of itself. So it's something like WASM bundles, where you can have bundles of a WebAssembly binary that contains other WebAssembly binaries inside of it, and can then instantiate them internally. And you can get integration not only into the ES module system, but between WebAssembly modules themselves, and leaning into the existing ability for WASM to treat imports as capabilities. And then this other one, which is also fairly technical, is that there's this shared nothing linking boundary. So all calls are effectively serializable, and there's no need for cross-thread GC. And it's a fairly technical point, but it's an important one in terms of the design of the model and how it relates to things like WebAssembly GC. So with those features of the component model, everything that this glue module is doing can then be done in WASM. And this is how you would write it in the component binary format. So this is WAT, which is a representation of that WebAssembly component binary. And using those features, you could then get something like the high-level glue itself being subsumed into a WASM-based format. Right. So then the other side of this is you wanted to define these nice high-level interfaces. And the way we do that for the component model is using WIT, which is these WebAssembly interface types. So it's a specific interface language where, for example, for ESBuild, you might want some transform options. At the very bottom, you can see there's that export transform function. So in this example, transform is going to be a function taking a source string, taking some transform options, and then returning a result. And the transform options, we can have a set of optional bools. So when you call it in JavaScript, the bindings can be automatically generated, and you could sort of pass a native JavaScript string. You could pass an object that represents the different options. And then you get that kind of ideal of something that represents, looks like a normal JavaScript interface, but it's actually written in this language agnostic way and can be embedded in any of these different environments. So instead of having a JS glue code loading WASM, we can have WASM with WASM loading WASM. And when we're looking at sort of what this means for dependency graphs and things like NPM, you can imagine that you could even have WebAssembly components just existing as whole packages on NPM, and then you abstract them out, and you end up with this idea of like WebAssembly first registries and WebAssembly first runtimes. So there's a lot of really interesting ideas there as the kind of proposal potentials develop. So I'm just going to talk very briefly about WASI and then going to get to the demos, which will hopefully work. So WASI is currently in preview 1. And this is something like a systems language for supporting POSIX-style APIs for WebAssembly today. And WebAssembly preview 2, WASI preview 2 is being updated to be component first. So WIT-based standard interfaces using that same kind of WIT syntax that I just introduced. So standard interfaces written in these component model first semantics. and the components of WASI Preview 2. The base level, we have WASI IO, so that's things like polls and streams, streams being really fundamental functionality, and then the system API is clocks, random, file system sockets, and then some higher level APIs as well, so WASI CLI and WASI HTTP. And yeah, hopefully I will aim to clarify it in a little bit more detail when we get to the demo. But yeah, so the JavaScript toolchain for WebAssembly components is a project called JCO. And what this provides at the core is a sort of a transpile workflow for WebAssembly components. So you can take a WebAssembly component, transpile it, and you would get something that you can run in existing JavaScript environments. So it will directly create all that glue code, and then you can directly import it as if that component was supported natively. In addition, the JCO project also provides some JS native component APIs. So for example, you can use it as a dependency on NPM and have access to a bunch of component tools. And then also providing first-class support for WASI. Okay, so I'm going to dive straight into the demo, and hopefully that'll give a lot of these ideas a little bit more context. Right. So here's the demo application that I've set up for this, and what we're running here is WebAssembly commands. So WebAssembly command is like a normal command line application. It's got a main function that runs from beginning to end. And we can run these commands in the terminal. So here I've got some files in the file system. And I've got a WID file to demonstrate some of my WID syntax. And I've got some basic terminal commands. What's special about this demo is that all of these, everything here is implemented using WebAssembly components. So for example, if I want to use a new tool like WASM tools, it's going to be dynamically loaded in as it's used. So let me just clear the network tab to demonstrate that. If I do WASM tools print that, so I've got a WebAssembly component as a local file in this local file system. And when I use WASM tools, it's actually dynamically loading in that command component, running it in the browser dynamically, and then executing it in that same shared system. And it's attaching to the existing file system and standard IO, et cetera. I can also dynamically build something. So this is the project that I'm running here, and I've got a local server running in the background. But say, for example, I cloned this Rust calsay application off of crates.io called charasay. So say I want to build this application and run it in my existing command app. So let me build that with cargo. So I'm going to say cargo build target WASM32 WASI. Build it for release mode, and that should do it. This does a normal WebAssembly core build on WASI Preview 1. I want to now create a WebAssembly component for this application. So what I'm going to do is use JCO new. Normally you'd use WASM tools new, but there's a bunch of options and flags which can be difficult to remember, so I've just got a wrapper for it with the JCO tool called JCO new. I'm going to point it to that build binary that we just built for charasay.wasm, and I'm going to build it as a WASI command, which will say this has got this life cycle where it runs a main from beginning to end. And I'm going to output that as chara.component.wasm. So I've now built a WebAssembly component dynamically. And if I want to run this component, I can use, I can actually just install it into that existing application. So I'm going to say install chara as, I put it in the commands folder, charasay chara.component.wasm, I think it was. I'm just going to verify that's correct. Yep. And now if I do charasay hello, it should download that binary that I just built, run it in the existing application without me refreshing it, and it should be linked into the system. And there you go. So we've just built that binary and loaded it into the page, and there it's being loaded dynamically in the network console. So that's the demo of browser commands. So what's going on here Well, I've got this application that has a script type module tag in it. I've got the terminal implemented in Xterm.js, which is the same terminal VS Code uses. And I've then built a shell in Rust. And that shell is just executing line by line, and it's got some sort of integration with loading components dynamically and things like that. And then it's loading all of these individual tools as we're using them. And all of this, what makes it a single system is it's running on a JavaScript implementation of WASI Preview 2 in the browser. So it's a component-based implementation of the system that includes the support for the file system virtualization, clocks, random, streams, and the CLI behaviors. And because everything is linked against that single shared system, it gives the sense that you have this sort of like operating system in the browser, and that's what gives that, that effect. The next demo I'm going to show is what we call reactors. And reactors are like what you're more familiar with in terms of like how you'd use a library normally. Instead of it being a main function that runs from beginning to end, with a reactor, it's more like a library where you can just call functions as you need them, get return values, and you can almost just directly replace the term reactor with library for the most part. And to demonstrate the reactor case, I'm going to go back to a simpler version of this demo that doesn't have as much features. It's a much simpler setup. Here's the HTML page, as I showed in the previous slide. We've got an import map setting up some mappings that represent that system interface, the script type module tag, and then we're setting up the standard out and standard error to point to the terminal itself. And so how do I implement that shell? Well, the shell itself is a reactor component. So it's a library that's built and has this single function execute to execute each line of the REPL. So I'm going to go into that shell application here in the local shell folder, and I've built my shell as a Rust application here. And here's the WIT file that represents that shell. It's got an initialization function and an execute function that executes each line of the shell application. And to build that component, I've got this Rust application that generates bindings against that WIT file and then implements these init and execute methods. So when we think about what it means that we run a command that takes a line and then can call another tool, you can see here is a very simple example of how echo is implemented, where you can just say, well, echo, you just print a line directly in Rust. So let's see if we can implement WASM tools, a very simple command like I showed at the beginning. So I'm going to add a WASM tools command in here. And when we write the WASM tools command, we want to check what the next argument is. So I'm just going to quickly fill this in. We're then going to match on that command. And this is where I have to really hope that my demo works correctly. So we did WASM tools print. And the next argument that I provide is going to be the file that I want to print off the file system. So we're going to do fs read. I'm not going to add any error handling. And then we're going to want to call WASM tools. So how do I call WASM tools from within this component? I have to update my WIT. So you can think of the WIT a little bit like the TypeScript type of the world, of the component. And in this case, I've already set up a WASM tools WIT file that I can just import into my component. So I'm going to say import local WASM tools tools. And by adding that import, I will now have if you look in this reactors folder that I've got over here, I have an existing WASM tools component. So I'm now importing that existing component. And in my Rust code, I can then use that imported component. So let's use local WASM tools tools. And this is an existing, I can actually just demonstrate the WIT for this. It's in my WIT deps folder, WASM tools, WASM tools. Here's that actual WIT definition for this dependency. And it's got this WASM tools print function that I demonstrated earlier here, typed as a function on the interface. So I'm going to call that from Rust. as a component. So tools print. I'm going to print that file, and then I'm going to, again, not add any error handling, and then I'm going to output that to the console. So that should be it. And I'm going to build this the same way I built the previous component, which is cargo build target wasm32 WASI. We're going to build that for release. And then we're going to do the same jco new command, but this time with WASI reactor to build it as a reactor. Target wasm32 WASI, release shell.wasm, and that's going to be my shell.component.wasm. So I've just created a component that imports another component called wasmtools and implements the wasm and uses the wasmtools print feature of that other component. All right, so let's get this demo running. And what I want to do is I want to tell the browser where to find this wasmtools component that I just output. So I'm going to use jco transpile, transpile this existing component into the local lib folder, and I'm going to provide a map configuration during that transpilation process, which is going to point the local wasmtools tools interface to the local reactor component that I built earlier in the wasmtools folder, which is called wasmtools.component.js as itself a transpiled component. And we'll see if this works. So in my demo application, I'm going to update my shell to load from shell.component.js, which was what I just transpiled from shell.component.wasm. I'm importing the shell, and then I can call the functions on the shell, which will be Rust functions that I'm calling in the browser. And let's see if it's working. OK, so I pointed to the wrong wasmtools component path. Let's have a look what the problem is there. So I added an extra. OK, so I missed the S in the reactors map. So I'm just going to go and rerun that command with the plural on reactors. OK, it's still not finding it. Let me just double check that pathing. So reactors, it's in wasmtools, and it's wasmtools.component.js. I've got two wasmtools. I should only have one wasmtools path in there. So it's going to be reactors, wasmtools, wasmtools.component.js. There we go. And it does not provide an export name print. OK, that's the last bug. And the reason for that is that it's actually an interface called tools on that module, which means that it's an exported object interface. And I can actually show you what that looks like inside of the reactors folder. Here is the wasmtools component. And you can see it exports a tools object, which has all of those functions on it. So I needed to point to that actual tools object. All right, and there we go. We've got it working, and I should now be able to write my wasmtools print command, which is one component calling another inside of the browser as if they were two native components. And you can see it's correctly executing these two Rust applications are talking to each other through components in the browser that are both individually transpiled into JavaScript and core wasm. OK. So note to self, stop doing live demos. But yeah, so we had this main shell reactor components importing other things like ls and wasmtools. We can build them all as individual components. And so we have something like a module graph like this. And we transpile that module graph to something like this. And we've still just got a whole bunch of glue code. But it's glue with a future standard layering. And that's the benefit. Now, on Node.js, we have support for WASI Preview 1 right now. Node.js, one of the limitations of Preview 1 is that you can only have a single WebAssembly application talking to a single instance of Preview 1. So in this example that I've been showing, we've got a whole bunch of components that are all talking to the same system. And the definition of what it means to have a single system is that you've got a single implementation of the system that's running a whole bunch of applications on that system. So sharing the WASI instance is what it means to have a shared system. And as soon as you have custom WASI virtualizations, you have a virtual system. And this leads into the idea of what it means to virtualize WASI and what it means to run virtual systems, and this concept of virtual platform layering, where I can create a virtualized file system, which I was running in the browser, and you can layer these things on top of each other and have layers of things that have their own internal file systems, so that you can layer these virtual platforms in ways that can talk to each other and remain portable. And there's some project work for this in a project called WASI-Virt, where you can actually build WASI itself on WASI, and then you don't even need a browser virtualization of the file system because everything can just run inside of the WebAssembly format itself. So I was running an implementation of WASI in the browser written in JS. You can imagine just building that entirely into the whole component itself, virtualizing it in, and then you've got a component that virtualizes its own file system. All right, so that's the Blitz overview. Some of the upcoming milestones that we've got is going to be the Preview 2 release coming early 2024. It's supporting WASI CLI. It supports both commands and reactors for these POSIX-style applications. WASI HTTP is another specification that defines these kind of edge services, the ability to do fetch in WASM and write proxy servers. And this is obviously the interest that a lot of companies have in terms of running these edge applications. Preview 2 feature revisions will follow, and then WASI Preview 3 will be native async support. So I hope that gives you a fairly good idea of roughly what's involved. So the idea is to be as illustrative as possible, so that hopefully it tries to give you some tangible sense of what's involved with these specifications. But yeah, thanks very much for listening. And if you want to check out the projects further, you can follow these links.